Here, we want to derive the reduction formula for integrating powers of secant. So we'll start with an integral that is just a power of the secant function, and we'll use some arbitrary power n for the sake of setting up this formula. Now, the main point of this formula is integration by parts, so we want to look at this function and think, is there a part of this that I know how to integrate? The answer is yes. We really like integrating secant squared, because the integral of secant squared of x dx is just tangent of x plus c. And so I like integrating secant squared, so I can rewrite this integral as the integral of secant to the n minus 2 power of x times secant squared of x dx. Now we're going to do integration by parts here, and we're going to pick this complicated thing here to be our u, and because we know how to integrate secant squared, this will be our dv. So we'll have u is secant to the power n minus 2 of x, and dv as secant squared of x dx. This means that v is tangent of x. And then du we can find by the chain rule. This is a power of the secant function, the composition of functions. The derivative will be n minus 2 times secant to the n minus 3 of x. That's differentiating the to the n minus 2 power. And now I need the derivative of the inside. Well, the inside is secant of x. Derivative of secant is secant times tangent. I can put those two secant powers together. Give me that du here is n minus 2 secant to the n minus 2 of x times tangent of x. And now I can write out my formula. My formula says that the integral of secant to the n of x dx equals uv secant to the n minus 2 of x times tangent of x, and then minus the integral of v times du. So tangent of x times this entire du expression. I can combine some powers in that last term, putting the two tangents together to make tangent squared, as well as bringing the n minus 2 outside the integral. The expression that looks like integral of secant to the n of x dx equals secant to the n minus 2 of x, tangent of x, minus n minus 2, integral of secant to the n minus 2, tangent squared of x dx. Now at this last bit, we can apply our trig identities, because we know that 1 plus tangent squared of x is secant squared of x. We can rearrange it to say that tangent squared is secant squared of x minus 1, and plugging that in here is going to give me integral of secant to the n of x dx on the left side still equals our same first term minus n minus 2 times the integral of secant to the n minus 2 of x times secant squared of x minus 1 dx. I can split this last integral into two separate integrals. So the integral of secant to the n of x dx equals our first term again, minus the first term, which is n minus 2 integral of secant to the n of x dx, and a second term plus n minus 2 integral of secant to the n minus 2 of x dx. I have a plus sign here because the minus sign here and the minus sign here canceled out. And now we see something that looks a lot like other integration by parts results we had before, the fact that the term on the left and this term on the right are the same integral. So I can add the one from the right over to the left. I'm adding n minus 2 times it to both sides. So my result is that I end up with n minus 1 times the integral equals my remaining two terms. And then I can divide both sides by n minus 1 to get to the final reduction formula, which is that the integral of secant to the n of x dx is 1 over n minus 1 secant n minus 2 of x tangent of x plus n minus 2 over n minus 1 integral of secant to the n minus 2 power of x dx. Now this works for any n you would want, but for the case of problems you want to solve with this type, we really only want to use it for odd powers of n. If it's an even power of n, we have other techniques for evaluating the integral and don't need to go this route, but it would still work. But for odd powers of n, the point is I start with, say, secant to the fifth, I apply this formula once, get down to secant cubed in the integral. And this term is not an integral anymore, it's all taken care of. Then from secant cubed, I go down to secant to the first, and we know how to integrate secant to the first. So this reduction formula lets us go from higher odd powers of secant down to lower odd powers until we get to n equals 1, and that we know how to integrate. So that's how you would derive this formula for reducing the power of secant in these sorts of trigonometric integrals.